Hello. I think this is live now, so please comment in the chat if you if you see this. If you can hear me, that is. Um, I'm not sure. I think this is live, but we'll see what happens. Okay, Jason and Mustafa, I can see you, but I'm not sure if you can hear me. Perfect, fantastic. That's exactly what I wanted to hear. Hi guys. So, today in this stream, I wanted to go and just outline the trig graphs. If you comment in there, I will be able to see it, but I will probably respond 40 seconds after you comment. So there's a bit of a lag. Sorry, guys. Fantastic. So, um, I wanted to talk about the three trig graphs that we have. The first trig graph that we have. If you have any questions or comments, just put them in and I'll respond to them as soon as I can, but it'll probably be about 40 seconds after you've asked. I'm not going to delete this. No, this will stay on for as long as I can. And thank you, Mr. Jup, for hanging out. This is going to be super cool. So, I'm trusting you can see this. A sine curve. I've got one here because I can't draw. Sometimes I can, other times I can't. But a sine curve is really, really useful. It is used in physics all the time. And the main thing about a sine curve is that it repeats. And they repeat every 2 pi. This is the standard sine curve. And this is called the period. How much it repeats is called the period. So I'm going to go with the period for this function here, this trig graph here, is 2 pi. But we can change the period and we can make it stretch out and compress, and then this 2 pi just becomes what it was, but it doesn't matter. So there's a few things. So there's the period. How long does it take to do one revolution? Then there is a thing called the amplitude. That is how far from the middle line, the curve goes. Okay, it goes above and below this middle line, but that is the amplitude. Another thing is the position of the start. For a sine curve, at the start, this is the origin. But we can shift it along, and this point and this point move along, but it's always good to track where that point is. Okay, so for a standard sine curve, we have the equation y equals, and again, amplitude is green, and we're just going to write the sine, and then I'm going to open some brackets, and the period we will write as x minus c plus, and I'm going to just change the color on this one here, and I'm going to change that color to purple. D. So that is the standard equation. All right? B is not the period. B is this funky weird thing where B equals 2 pi out of over the period. Okay? Because it's a ratio of 2 pi. So we actually call the period T. So whenever you see B, think of it as 2 pi divided by the period. And so in fact, B is the frequency. Similar ideas, but not the same. Oh, hi, Dr. Hoffman. Welcome along. Okay, so this is a standard curve. A is how far up it goes, and the standard A is 1. The standard B, the standard period, is also the standard period is 2 pi, and so the standard frequency is also 1. The standard shift is 0, and the standard vertical shift is also 0. And so this is what gives us our standard sine curve. Now, this kind of information can be transferred to be exactly the same when we have a cosine curve. So for a cosine curve, I'm not going to rewrite everything, but all I'm going to say is we have y equals a cosine brackets. Remember, b is not the period, it's the frequency. X minus c plus, where d is the vertical shift, right? D is the vertical shift and c is the horizontal shift. Now, these are the equations we use. Your question might be, why don't we do the same for a tan function? And the answer is we do. We can. But the tan function is ugly. The tan function is quite ugly because it doesn't actually follow a nice pattern that we like. It goes off to infinity and then comes back up from negative infinity. Then goes off to infinity and comes back up from negative infinity. And so it's not a function that we typically use very often. And so that's why we're not going to look at modeling tan functions. Okay? Tan functions are really useful when you've got algebraic situations or trying to do things, but for modeling, tan functions are not very pretty. Okay. So what I'm going to do is I'm going to try and do a question where I look at and see if I can find out all of these factors, all these parameters of this function. Okay, so let's just navigate back. Okay, so here we go. And I'm just going to use sine for what I have, okay? Because I feel sine is quite easy to work with. So here's my function. Y, ooh, that's big. Y equals a, nope. Y equals a sine brackets b x minus c plus d. Now let's try look at this and see if you can figure out A, B, C, and D. I'm going to wait a minute. If you think you know what A, B, C, and D are, please type them in the comments, in the chat. Go A equals, B equals, C equals, D equals. If you think you know. I'm going to wait. Yep, Jackson. A is the amplitude. That's correct. B is the frequency, C is the horizontal shift, and D is the vertical shift. But let's look at our graph here. A is the distance between the top and the middle. And you can see the middle is at 4. So what's this distance here? Well, it goes from 4 all the way up to 7. So A is going to be 3. Okay, well, if A is 3, can we work out what D is? D is the vertical shift. How much has the middle of this graph moved up? Well, the middle of the graph moved from 0 all the way up to 4. So D is 4. Fantastic. I'm not sure how to say your name, but you're correct. And so now the C. Where is the C? Well, because it's a sine curve, I want to look for where it looks like the start of a sine curve. So this part here. And for me, I can see that in here. So that point there, what's that value? That value is 6. So I'm going to say C is equal to 6. So I say C is 6, A is 3, D is 4. B is still the one that we've not yet figured out. But B is the time it takes to go from the top back to the top, or the middle back to the middle, or, well, I can just look at this part here. That number there to that number there. That's when they're at the same height. In here, the period is that distance there. The period is that distance there. So C can't be 1.5 because we want a sine graph and it's going up. And so it only goes up at this point in here. Okay, so B for me seems like it's going from 1 through to 11. So I feel as though that B is 2 pi on 11. Yeah, you might be thinking, yes, you might be thinking cosine, in which case you have to do some other shifts. So for me, I've got A is 3, B is 2 pi on 11, C is 6, and D is 4. Now for me, that will be the equation. Y equals 3 sine 2 pi on 11 minus 6 plus 4. Okay, that's not that hard. But it's really important to figure out where your middle line is and where your shifts are. I'm going to ask you to try and do the same for this one. Okay? See if you can figure out what A and B are. And I'm going to actually go put this one right next to it too. And so that you can actually try both of them simultaneously. Okay. So try this one and then try this one. And see if you can just list off. Ah, you're correct. Yes, it's 10. How did I say 11? Oh, because it's down the bottom at 11. See, we catch mistakes very well. Well done. Yep. Thank you, Jason, and Mr. Jupp and Joshua. Yeah. We all make small mistakes. Good. Yeah, it's 10. You're right. So let's try this. So try these two and see if you can list off what A, B, once again, is 2 pi on the period. 2 pi on the period. And C, and just a little bit. Give me the left one first, and then give me the right one. Who is the TV king? There are some weird people on here, man. But anyway, so try this out. See what you get, and see if you can make it make sense. So in trigonometry, it's really important to give yourself time and to give yourself a pattern to follow so that you don't really make too many mistakes. And going back to what Jackson said earlier, watch it that you don't accidentally try to graph a cosine when you're looking for a sine or the other way around. I could easily model these with cosine curves, but the way I've set up these questions, I want them modeled with sines. But if you could figure out cosine, that would work. Is your name Sefer? Yeah, that's correct. I like that. Oliver, I also like that. That looks pretty good. Yeah. A is 3. Yep, because the distance between the middle and the top is 3. D seems to be at this point here, which is -1. So that's fantastic. C seems to have moved over 1. And B seems to be 2 pi over, well, this distance here, which is 3. That seems to work. And what about the next one? Think about it. Equals 3 sine 2 pi on 3 x minus 1. This time it's a minus 1. Okay. So that one works, and that's how we figured that. See if you can try to do the same kind of stuff on this one. And welcome, Connor. You're allowed to relearn trig whenever you want. And James, Jackson, well done. I'm very, very impressed. Yep. I don't know what Skyrim is, but sorry, don't at me. I know what Skyrim is, but I don't know where the emblem is. Send me a picture in an email. So this one, once again, the amplitude, that part there is 2. The D is how up that is, and that seems to be at 4. Once again, C, I'm going to look for a nice one. I can use 3, but I could actually also use this 9. It doesn't matter. C could be 3, it could be 9. I could use C as 0 because it's a negative sine curve. Yes, that's fine, but I'm just going to use 3 because I don't want to put I don't want to put negative amplitudes because I feel as though it will change how I look at these, and I kind of want to always keep positive functions. So the period is all I'm looking for, and so the period here is this thing here, and once again that's going from 3 to 9, and so that's 6. And so my function will be y equals 2 sine 2 pi on 6 x minus 3. I could have used 9 brackets plus 4. Now for me, this is how I would figure out what trig functions need. How to model a trig function, how to find the function of it, and make sure that I'm looking for these special three things. I think it might be time for you guys to try a few more. So there are questions in your book that deal with this. There are questions in the workbook that deal with this. But forming models is really important with trig graphs, and knowing what they look like and how to manipulate them is really, really important. Are we able to simplify these pi's, or do we keep them as 2 pi of x? You could simplify, but I'm just choosing not to for now, because later on, when you start to look at comparing them, so if we look at this one here, 2 pi on 3, and this 2 pi on 6, it's easier to compare that this one is twice as big as this one, right? 2 pi is twice 2 pi on 6, which is very, very useful. Is it possible to rotate trig functions? You could rotate trig functions, but I don't think that's necessary right now. If you're saying rotating as in changing the axis so that, I don't know, they look like this kind of thing, I don't know why you'd want to. I feel as though a function like that would be very scary. Maybe in Skull, but I wouldn't go there. Yeah, this video will be available post stream. I'm keeping this up. So I wanted to then sort of ask and check you guys, if you can model this kind of thing, then you should be able to model them with this cosine curve too, because a cosine, sorry team, it's just gone a bit. A cosine is the same as a sine, but it's just shifted back pi on 2. So if you did the same as a sine model, but added pi on 2 to your angle, you will probably be able to get the same model. So what I would like you to do is, for our three functions that we've just modeled, see if you can write the equations in terms of cosine. Okay, that's what your task is. And I just want you to list out what A, B, C, and D are for each of them, if you were to model them with cosines. I think it's an interesting exercise trying to reframe a model in terms of another function. See what you get, and we'll have a chat real quick. I'm hoping the stream is still live. I can't see any comments in here, so I'm assuming you're working. But see if you can convert this, and the other one, which I can't seem to get on the page, but I don't want to move it around too much, in terms of cosine. Would A, C, and D change? Would B change? Is it A that stays the same, B that stays the same, and D stays the same, and you just have to figure out how C changes? It's a really interesting conversation. So think about it, have a go, and I'll just wait, and then I'll come back with some more graphs for you to look at. Okay. Right, yes, thank you. I will fix that. I forgot to transfer that down. Yes, yes. Thank you, Jackson. Sorry. It's probably, the fact that I've been in isolation for so long, my brain's falling out. But good catch. Okay. Okay, so that's an interesting conversation about plus and minus. Feel free to discuss in the comments as to whether it's plus or minus. Um, but I feel you'd find that if you move towards the left, it's plus. If you move towards the right, it's minus. And see how you'd compare that as you change. Okay, I'm about to give you a few more problems. I'm hoping that you're working at home, so that's why there's so little activity on the thing. Yep. So, Oliver, what did you notice was the main change from the two models? Yeah, Harry, well done. Good conclusion. Only see changes because sine curves and cosine might decide actually I'm going to only use sines or only going to use cosines because it might make more sense. All right. Okay. Um, are we all happy with Oliver's answers that he's producing? Because I'm not sure everyone is seeing them. And so, yeah, okay. So, could you please move my screen to the right? Yes, I can. Yes, I can. Yes, you can use Desmos to check your answers. That's wonderful. Yeah, use Desmos to check your answers. You have more power back there than I do here. This is fantastic. This is why I'd love to use Desmos. Oh, that's right, Connor. You can use the emergency phase shift. If you remember what we talked about in class, yes, pi on 2 will shift things. And so that pi on 2 is a shift of 90 degrees, and that's how you shift between cosine and sine. Okay, Oliver, I think you've seen enough. I'm going to just put 3 more questions down here that I want you guys to adventure through. Okay? Um, um, so let's hope this works. Okay, there we go. Okay, they will come onto the screen in a second. They are a little higgledy-piggledy, but that's okay. Okay, see if you can find the models for these 3 graphs too. Okay, so can we reach a conclusion as to whether it's plus 1.5 or minus 1.5? doesn't matter. Don't you subtract pi from c? Well, to convert it from cosine to sine, you're subtracting pi on 2 from c. But that's only if your period was 2 pi. If your period was not 2 pi, um, if your period was not 2 pi, then you won't be able to do that. I'm really struggling here, guys. Just give me 1 second. Can you zoom in on these if possible? Fantastic. Yes, sure. All right. Is that zoomed enough, or do you want me to zoom a little bit more, Max? Is that okay? There we go. All right. Sorry, guys. I've never done a live stream like this before, so we're testing it out. Okay. So I've zoomed into these two. Forget about the third question. We'll get to them. But yeah. Can we tell me what A, C, and D are? Yeah. I think you're right there, Jackson. Yeah. Just do these two. And then once again, A, B, C, and D. Perfect. So once again, try to figure out what's really important. And check yourself, are you going to use a sine curve or a cosine curve? Which makes more sense? Okay, because a sine curve before was really nice because it was going through at nice intervals. This one, cosine curves might be more useful. I just want to say I'm going to end the stream in about 5 minutes because I've got to prepare for my level 2 stream. Sorry, I just burped and it's been recorded. Oops. So we'll just leave this here and I'll give you about 4 minutes and then I will wrap this up. Okay. So in this graph, I am going to look at use a cosine curve. Why? Because these peaks seem to be on whole numbers, whereas this part doesn't seem like it's on a whole number. And that's just my preference. And same here, you know, this seems to be on a whole number, whereas this doesn't. And so I think it'd be easier, or sorry, this kind of does, but vertically it's not on a whole number. And so I'm going to use cosine curves on this. So my C is going to be slightly different. So A, once again, is going to be that distance there, which is 3. Yeah, I'm okay with 3. Okay, let's go to D. D is the vertical shift, and once again, I think the vertical shift is 4. C. C this time, I'm going to start. What is the start of a cosine curve? Ooh, Lord. Start of a cosine curve. And the start of a cosine curve, I'm going to redraw that again. Okay, is going to be that point there. So for me, C is going to be the apex, which is at 1. So C is 1. And then B this time, let's see, Oliver, yeah, that seems reasonable. And you reckon it goes 5? Yep, seems perfect. So 2 pi on 5. Outstanding. And so once again, I'd write the model, but this time I'd use cosine. And same for this. Let's go. A is equal to, for me, look for the middle and go, there we go. What's the middle? I think that's about 3 as well. Okay, if you don't get a chance to look at the middle, you can find the difference between the top and the bottom. And if that distance is 6, then what's half of the 6 is 3. So sometimes it's not as easy with your eyes. Okay, so A is 3 once again, and D is equal to, well, this time it's also negative, and C, this time I'm also going to use 1, and then B finally is going to be, for this one here, this distance here, from 8 to 1, it's going to be 7. 2 pi on 7. So it's 2 pi, so 2 pi on 5 for the first graph. Oops. 2 pi on 5 for the first graph, but 2 pi on 7 for the second graph. Whoa. C is negative 1, Dr. Hoffman. No, I think C is still 1, because in my cosine graph, my equation is still A equals 3 cosine 2 pi on 5 x minus C plus 4. And here, y equals 3 cosine 2 pi on 7 x C, which is 1, minus 1. So just be careful. In our model, we are always using a minus sign in here until we subtract a negative or something. So you've got to be a bit careful, see how it goes, but it's really important that you model carefully. I'm just going to add one last bit of information before I check out of here. So you can just check that if you want, but the last piece of information is sometimes if you're given some information, A is equal to the maximum minus the minimum divided by 2. D is the average, so the maximum plus the minimum divided by 2. C is the horizontal shift of start. Remember, if it's a cosine curve, you're looking for the top, and if it's a sine curve, you're looking for that point or that point. And then finally, sorry, I don't know how to delete that. Okay, cool. C and D once again. I've got it so that if I draw really nice curves, it makes circles for me, and now it's not actually helping me. B is 2 pi divided by t, where t is the period. Okay, so sometimes this is a little bit more useful. Yes. Okay, so Dr. Hoffman, sorry. The way I always do it in the model I've always used minus C, but if you use plus C in Dr. Hoffman's class, make sure you figure this out, okay? Yeah. Once again, and supporting what Mr. Jupp is saying, if C is the value from the origin, it's the first time you get a max. And if it's for a sine curve, it's the first time you get to the middle going up. Okay, I think I'm going to leave that there. I think we've gone through a lot. This was very, very, very interesting. It was very different, but thank you for coming along. Please, please, please comment if you have any questions about this, and we'll try to get back to you. But I feel as though that this was productive. Okay, thank you, team, and I'm going to sign out.